So something I wanted to talk to you about was essentially with all like the cuts that are happening within the government right now. A
Mhm.
headline that kind of caught my eye, and for the record, I think everyone's kind of put this together, is that I purposefully do not read the articles. I only read the headlines so that I can ask them here, right? And so I saw this headline talking about the National Institute of Standards and Technology and how
Yes.
they're responsible for critical atomic measurement data.
Yes.
What does that even mean? Okay, for me, I'm like, all right, what's the most critical measurement data from an atom? They're small. Like, you know what I mean? It's like,
Where should we start with this? All right, let's try and make this a little broader. Atoms are, for the most part, pretty predictable to a point. We now when you get into quantum mechanics, they're not. They do the opposite. They do
right.
spooky stuff no matter what's happening. But a finite number of atoms will make up a molecule, and a finite number of molecules make up a thing. So it's pretty easy to like measure with an atom, atomic
Right.
measurement units. Like it's like, okay, this this many atoms equals this much mass. This many atoms does this. So we all know what an atomic clock should be, kind of based on how it's talked about, but most people don't actually know what it is. So what you're doing is measuring the degradation of an atom in quartz over time, and that's why quartz was such a big deal and all
Is
these
that why
other.
you have
That's
like
why
half-lives and stuff?
Half-life is a little more complex than that, but
Oh,
yeah,
okay.
that's the amount of time that it takes for half of the available particles in a given sample to decay to something else.
Okay.
So it's, or at the molecular level, how much a molecule will change into another molecule or stop its effectiveness. So half-life is something that we can measure mathematically pretty easily, but an atom, like I said, is pretty predictable, depending on what we're doing with it. Now, like once we get down to actually how atoms act, like I said, then you're in a quantum realm and things aren't predictable anymore. That's why quantum mechanics is so weird. But an atomic clock uses the spin rate and the position and a bunch of other measurements from an atom to kind of tell time. Like 1 second equals 1 second. So we're sure that
Hmm.
one measurable second using an atomic clock is one measurable second. And it will always be, if you look at this clock, during the whole nuclear degradation process, which takes hundreds of millions of years, this atom will just stay spinning at 1 second the whole time. I'm really simplifying this process. Atomic clocks are actually super interesting to dig into. It's what powers the clock within our computers. So any computer that has when you hear clock speed, oh, how many gigahertz? Well, it's based on a quartz crystal that's sitting on your motherboard somewhere that's actually based on power. It spins at a certain rate or vibrates rather. So NIST, the National Institute of Standards and Technology, uses atomic measurements to measure all kinds of stuff,
Right.
not just time, but time is one of the most important pieces of that because if we can't measure time, we really don't have anything. There are a lot of people running around, and Shane, you and I've talked about this before. It's like time doesn't exist; it's a construct. All right, well, you tell that to an old person, but it's the perception of time might be a
Hmm.
construct, but time itself is a physical law within the universe that things move this direction, entropy, whole different conversation around that. So when you're no longer using kind of the basics of atomic chemistry to
Hmm.
measure things, your accuracy is going to drift. It's just not going to be the same. I was fascinated with atomic clocks when I was a kid because, as Shane puts it, I'm older than dirt. So when I was a kid, you didn't have like a digital clock. You didn't have your phone that was set off some clock in Cupertino somewhere or in San Jose somewhere. It was like everything was based on the same time. That's why in network transmission, when you were first networks were being built, the internet was first being built, having NTP, which was network time protocol, to make sure all the clocks were in sync was really important. Otherwise, then things would arrive differently and the machines would get confused because time was so critical to how you measured everything. So it used to be a phone number that you could call, from your rotary phone. It's like on your wall. You call the phone number, and the time at the beep will be, and it'll give you time, and that's how you set all your appliances and things in your house and set your watch and stuff like that. It was all
That's
based.
crazy.
I know, I know. So it was all based on an atomic clock. That and some really important places had atomic clocks like MIT and Caltech and things like that So each time zone kind of had an atomic clock, and then you'd measure them against each other and be like, oh, there's this much drift. And that was how we figured out when the astronauts first went to the moon during the Apollo missions that there was actual time dilation at work that Einstein had hypothesized because we had an atomic clock on Earth and we had a similarly keyed clock that was on the spacecraft. And when it came back, they were off by a few milliseconds, which means the astronauts had actually aged less than we did because they had accelerated to such an incredible speed to get to the moon that their mass had increased and time had effectively dilated and slowed down for them by a
Wait,
very
so the bigger
small.
you are,
The more massive you are, that's
all
different
right,
than.
I'm
So that means
massive.
that the rate you keep going, you're never going to age. But
I like to I prefer to call it a gravitationally challenged.
so measurements, the concept of studying, I never thought I'd use this word in
Mm,
real conversation, the concept of metrology, which is understanding the metrics behind
mm,
things, the
okay.
studying metrics themselves is a really important factor for standards of any type. And using atoms and the math that's associated with atoms is a really accurate way of doing those measurements. So when you stop using the money that is required to use atomic measurements, there's always the possibility of drift. And that possibility, it's probably pretty remote at this point because there's a lot of different things that are keeping time. But that doesn't necessarily mean you don't need a gold standard, especially when you're trying to measure things at such infinitely small scales, like distance in space, you know, where we wouldn't have known. We wouldn't have been able to prove time dilation that
Right.
Einstein had hypothesized without actually sending astronauts at 20, 30, 40, 50, 100,000 miles an hour, and saying, oh, okay, this is what it is. This is the time dilation difference because we have this one clock and this other clock that are based on atomic spin and position and things like that.
Dang.
Don't screw it up, man. We got to measure stuff. Measurement's
So
important.
what I'm hearing is if we don't fund it, right, and then time drift happens, maybe it slows down, or like our clocks speed up because they're like a
Mhm.
mathematical, you
There's a
know,
difference. Yeah.
yeah, it's like it's not accurate. It's just doing like a time equation or something like that. Potentially, like on paper, you would live for longer because like the clock would say you live for like 80 years when in reality it's only like 77.
Potentially, yeah, but I mean, if we actually start generating drift
Hmm.
in measurements at hyper precise levels, not only does that kind of break science,
Okay.
because we need precision at a very, very detailed level. And when you're talking about precision that's like 2 times 10 to the negative fifth or negative seventh or negative tenth, like that's a picosecond. So
Right.
you're talking about things that happen at rates that are you don't have numbers to measure for. It's why I use scientific notation. But more importantly, and how it would impact kind of everybody's life is if we're off by a millisecond in network transmission,
Hmm.
this video doesn't happen. The two systems can't
Oh,
talk. They don't
okay.
believe the time is the same. And when they do that, and in modern networking, I mean, it's admittedly a very long shot for some of those things to happen. But so it's not like we're talking about a big requirement here. I'm not, I honestly, I don't know what the actual impact of not using some of these measurement techniques would be, but I do know that when you lose accuracy, there's risk, kind of
Right.
in all of these things that require that level of accuracy. So yeah, you might gain 3 years, but it might be back to sustenance farming because the network doesn't work right.
So, along like the the things of like time, I should say. So how do like networks actually like talk to each other basically? Like if they're going or if there's like a reference of like an atomic clock, right?
Mhm.
And networks need time that is like basically reference to that clock. Do
Mhm.
they just use the math equation or whatever to be like, all right, this amount of like, this calculation is exactly 1 second, and that's how they talk to each other? Or like, because they're not
That's a
constantly referencing some atomic clock in like Idaho or
No, no, they most networking devices don't check the time that often, depending on what they're doing. But when you're starting to transmit across bigger and bigger distances,
something.
the time that a packet left, a particular router or switch, and then entered. the domain of another router or switch and was, within the routing table within the switch, that or the router. Some level layer three switches have routers on them now, but that's an interesting and entirely different conversation right now. There's the time index and reference starts becoming more important for the processes that the endpoint systems are engaged in, not necessarily the network itself. So
Okay.
being off by a few milliseconds isn't a big deal, but the example of that is your phone. When you
Hmm.
pick it up and you send a message, if you're on iOS, the iMessage app timestamps that information within each of those packets and says, this is when this got sent. Not in each and every packet, but within
Right.
the frames that are moving through there. This is when this got sent. And then when the servers and things receive it, they're kind of checking all of that to make sure that nothing happens out of sequence, so that you don't get, because if things happen out of sequence, they're going to drop the packet and wait for another one, or, and there's a lot of protocols. There's a lot of really robust ways to protect that in modern networking. But the cascade effect is something that a lot of people don't think about in networking. So, how does it work? Well, the router, the big router, your central networking node, like for our office or for our lab or
Hmm.
anything like that, that router is not every packet or every time it sends anything, checking the time. It's got an internal clock, but it's going to set that internal clock anytime anything interesting happens. But power goes out, it's got to recycle, it's got a packet overflow or something like that.
Right.
It's going to set that clock by some other clock.
Okay.
Whether that clock is, a DNS server, or, a hub point that it's talking to, or a upstream router, or ultimately, some of the big clocks that are measuring everything, the atomic clocks. It's going to set its time by something.
Hmm.
So if that accuracy is off by a few milliseconds, then it starts creating all of these downstream effects that are ultimately more challenging. But as I said, networking is pretty robust at this
Right.
point. It'd be relatively difficult for some of this to go sideways, but more importantly is about the science. If you're
Hmm.
measuring things that happen in a 10,000th of a second, you need a pretty accurate clock. You can't just be looking at your watch. It's not going to work.
I don't know. My watch pretty accurate. What can I say? No, just
I
joking.
mean, yeah, the nerve conduction velocity of your eyes to your brain is less than that or more than that. So by the time you saw the number change, the amount of time would already have gone. It doesn't matter how accurate your watch is, your brain's not.
Dude, my brain is definitely not accurate. Of all the brains in the world, and even in this room, dude,
This is
my
the
brain
least
is
accurate one.
accurate. If there was a yearbook post for least accurate brain, I would have won that one, dude. Class of 2019, buddy. Shane Kirk, least accurate brain
Least
award.
accurate brain. That one, yeah, that needs to be your handle now. It's
Believe it
like
or not, I
Shane of
actually
the least
majored
accurate
in
brain.
brain accuracy at UC Davis. They said I had to switch majors, and helpless case.
Because you were the least accurate brain. You got it in the Davis yearbook too.
Yeah, yeah,
That's okay. I'm
exactly.
I'm the second least accurate brain. I measure everything.
Yeah. So something I wanted to ask you about was I feel like you've already seen this, but was scientists freezing light?
Yeah, yeah.
How, okay, I won't say how, because I've said a lot of dumb shit on this show. I've said a lot of dumb shit off the air. Like for those of you who listen, I genuinely like Matt was explaining to me what chemistry was, and I genuinely went, I'm gonna be honest, I thought chemistry was all about liquids. I genuinely said this. And so when I read the headline, scientists managed to freeze light. I was like, in my head, I'm like, oh, they put like a flashlight in the freezer filled with water. You know what I mean? I was like, I could have done that. But no, they're talking about like photons and all this stuff. They're like light particles that are tiny and they're frozen. So the question is here, how exactly do you, A, freeze light? And what does it even mean to freeze light? Is it just that now the light particles aren't bouncing all around the room? Because
Yeah,
they
yeah.
showed the picture of it or whatever, and it was like basically just looked like light was standing still, right? But isn't there like light particles bouncing off the frozen light
Yeah, yeah.
particle? You
So
know what I mean? To be able to
let's
see the light particle, like you know what I mean? I'm just like this whole thing doesn't make sense to me.
so light is difficult to conceive of anyway for us, because
Hmm.
we take it for granted, and second, it's one of the only things we can actually see in the electronic or electromagnetic spectrum. But light is a conundrum by itself because it
Hmm.
behaves as both a particle and a wave, the double slit experiment and things like that. So we're not entirely sure. We can't measure it. You can't put it under a microscope and be like, what does a photon look like? It's we don't know exactly what's happening. We got a pretty good idea because we do a bunch of mathematical equations and we do some experiments, and we got a pretty good idea that it behaves as both, and it hits things. It doesn't have any mass, but it's moving at the speed of light, which we could go on a bunch of conjecture about that, mass and energy, and also
Mhm.
Einstein's equation, which is the most fun equation ever. But if you actually think about it, it's just an enormous amount of energy. But being able to freeze something, first talking about freezing a thing, the concept that we have freezing is, ice and like
Yeah.
things like you get really cold and stuff like that. But thermodynamics is the application of energy in the form of heat, and how things move. That's not what it is, but that's what it describes. So when you freeze something, you're simply stopping or slowing movement. It's all you're
Mhm.
doing. Whether it's at the molecular level or the atomic level is a whole different conversation. But when you freeze water, all that H2O, that's the actual molecules that are in there bouncing around, doing all kinds of crazy stuff in the liquid state, you freeze them and they're slowing down. They're not moving
Right.
all that much. Now you keep going. Eventually we get to absolute zero, 0 degree Kelvin, and it's solid. It's still a solid when it's frozen. It's not totally a solid because there's always transition states in there and all kinds of weird stuff. Chemistry's screwy and amazing. Love chemistry because things are just, the
Yeah, I
science is
like liquids
bizarre.
too.
Yeah, I really like liquids. Get out of here. But and then the opposite is true. You apply energy, so you apply heat. And eventually that water becomes steam. The molecules become so excited that they don't even stay in a liquid state. They move into a gaseous state. The prevailing theory right now about light is that because photons, which are the particles that make up light,
Mhm.
theoretically, have the properties of both a wave, which would be the energy portion of them, and a particle, which would be the solid portion of them, that they should have some of the constraints
Okay.
that both a wave and a particle have. So particles with sufficient energy, with lacking sufficient mass, can pass through certain objects, which is why certain things are permeable by light. Energy can apply itself to things. When you run into something at high speed, that kinetic energy is that's transferred to that thing. Where if you have an unstoppable force and an immovable object, and they run into each other, you get a ton of heat, creates explosion, all sorts of crazy things. So light follows some of those same rules. That's what we're starting to discover. That's what that in my opinion is one of the coolest things about this science is that we're starting to understand that parts of light, photon itself, have to follow certain other cosmological rules, certain other physics laws that are appearing there. So that if you deprive light of enough energy, it stops,
Right.
which that to me is mind blowing because it means we're starting to see that both of the processes that exist there, or not the process, the states, the wave state and the particle state, are subject to the rules that are around it. Some of the interesting theories that led up to this was that light is subject to gravity at sufficient density. So when gravity is strong enough, you can bend light. And that's not just the black holes that are drawing light in, but also gravitational lensing, being able to see things behind heavy galaxies in the distance
Whoa.
because the light bends around them and we can see around them using gravitational lensing. So there's some really cool things that we can do, and or rather we understand about light. And now this experiment shows that we could do even cooler things. We actually kind of stop it. Now we're not, based on what I read, and there's a lot of, I haven't read the whole paper yet. There's a lot of conjecture about how they did it and things like that. But the at this point, peer reviewing and a lot of arguing is kind of showing that yeah, we can reproduce some of this. And in doing that, stopping light, so effectively freezing it, removing enough energy that it's not really moving anymore. Man, the possibilities associated with that, if we could continue to do stuff with it, are pretty mind blowing. It means that it's reacting like a particle. We're able to
Mhm.
do things to it, and we manipulate particles like crazy. We already
Right.
do all kinds of stuff. So if we can figure out how to manipulate light at that level, there's this concept in science fiction, which might actually become science fact about solidifying light. Creating it, if it acts like a particle, you could effectively increase its density. And by increasing its density, you can make it solid surface.
Mhm.
So you can make a light that you would touch something, actually carry kinetic energy with it. which would then break physics because that means that it have kinetic energy, but it wouldn't have any mass because it doesn't have any light particles, don't have any mass. So how would that work?
Mm,
So then we start asking questions that are bigger than
right.
that. So the short answer, how does this work? We're just depriving it of energy, that, and we already know that light has energy levels because during some certain radioactive processes that take place chemically, the particle that's ejected is a photon. This is what gamma rays are,
Hmm.
is photons that are,
Yeah.
pushed out from a high energy particle. So that we already know that, high energy photons can do crazy stuff. I mean, gamma rays obliterate even matter at certain levels, break it apart. So that's a photon that's doing that, which effectively has no mass. But maybe going back to our first, and this is purely nobody take this to the bank. This is late afternoon Matt who's just guessing at random
Just
shit.
conjecture.
Maybe if light actually has mass, but that or photons have mass, but it's so low that we don't have the accuracy to measure it. That's I've I don't know because then that blows up E equals MC square and that throws
Mm,
Einstein stuff out the window and things like that. I don't even want to start talking about that. I don't have the depth of physics at that point to have that conversation or be in that kind of air with scientists like that. But the possibilities associated with being able to actually stop the movement of a photon is just mind-boggling. Like the ability to do that. That's some science fiction shit. That's living in the future right there.
yeah, because like if a gamma ray, which is just like a photon or whatever that has no mass, can destroy things with mass,
Hmm.
essentially. If you were able to increase the density of a bunch of photons and then you find they do have mass, dude, that's like
Yeah.
Star Wars ray guns come to
Well,
life.
yeah. Well, yeah, but more than that, that actually starts bending the light speed limit theory. Because if something has mass that is moving at the speed of light, that means that an object that also had mass could also move at the speed of light. It would just require more energy. So then
See,
then
I'm
there's
thinking
some
Star Wars, and you're thinking like actual like game-changing level science. See the difference here.
that's but don't all of our 42 watchers don't get I was already thinking Star Wars. I thought ray guns a while ago. I'm just further ahead than where Shane is right now. But the idea behind energy is what would make,
Mhm.
the ray gun concept so interesting is that if you can compress photons, if you could make them start acting like existing matter, then there's the possibilities just explode exponentially.
Right.
Yeah, okay, but how do we do that? The one thing I did read in the paper so far is that the amount of energy and precision and things like that were relatively high to make this work. So it was not like you can just replicate it in your bathroom. This is a significant scientific experiment. But the result of being able to freeze light, now, I mean, there's a little bit of clickbaity there because you're not actually freezing anything, at least. I mean, you
Hmm.
are in the technical term, but a lot of people are going to do the same thing you did, which is like, oh, so you put a flashlight in a freezer. But I can freeze light too. But it's but the actual concept behind it is pretty mind-boggling. Is that
Right.
now, we've proven or we've experimentally seen that we can make light do things that we couldn't make it do before. And that's cool. There is a video that I watch pretty frequently that shows it's a video of light traveling at femtosecond frame rates. So you can actually see the light moving across the bottle that the
Whoa.
experiment was doing. So you can see the wavefront of the light because the frames are so fast. So that we're 20 years ago, 30 years ago, looking at something like that, we would have thought that was impossible. But now I think it was 5, 8 years ago or 8, 9 years ago when that video came out, you can see that frame by frame, femtosecond by femtosecond, the wavefront of light's actually moving forward. And this is just another iteration of that. Like now we're figuring out more about light,
Hmm.
and that's where things get cool because light represents a universal constant. We can't go faster than light. I mean, all of the current existent theories about traveling extreme distances are based around wormholes and folding space, and the interesting ideas around the three-dimensional travel in space and things like that. But the light speed is always kind of represented a wall. How do we do it? Well, we can warp space or we can move space-time, which is what, Star Trek theorized. And, now there's a couple of projects that NASA was working on actually building warp engines. But the amount of energy it would take to move those so astronomically high, it's like the power of a galaxy to be able to
Mm.
move a spaceship. So there's equations and understanding we don't have. And finding this, like, oh, we froze light for, nanosecond or whatever it was. I don't remember exactly what it was. Then that's cool. That could open the doors to other things. That's why science is so awesome, is where we learn things, we try new things that we didn't know before. And some of them are nuts, and then some of them are stupid.
Right.
But that's how science works, is you gotta try the dumb things along with the nuts things. And half the time it's not going to work, but the one time it does, you always hit a home run.
Yeah. I mean, it's the idea of like moving at light speed is insane to me. And like the amount of energy is like we think about like nuclear fusion and all these different like
Mhm.
energy sources and how like some people talk about how it's like the energy from the sun or whatever, like it's equivalent energy or whatever. But the thing is if you put it in perspective that like you need the power of a galaxy to move across like space at the speed of light.
Yeah.
Maybe nuclear reactors or fusion or anything like that isn't even good enough. Like, what's the energy source after nuclear? You know what I mean? What are those questions?
We're playing in a sandbox compared to cosmological technology at this
Hmm.
point, cosmic levels. And I mean, there's the kind of the standard growth theory in energy is, you've got your fission model, you've got your fusion model, you've got your matter antimatter model, and then you've got your 0 point model.
Hmm.
And 0 point energy has been played with in science fiction for a long time. Atoms move, even when they're at rest, even when they're in a solid, atoms are flitting back and forth in kind of a quantum state. And being able to capture the kinetic energy of that movement is what's frequently referred to as 0 point energy. So it would be a near infinite battery because we don't know what powers that. We don't know what makes those atoms move that way. And if we farmed that energy off of them, what would it do? Would the material break down? Would we end up with byproducts like we do with fission or fusion? Would we end up with a net product at the end of a balanced chemical equation? Like, well, I don't know. We don't know. We don't even
Yeah.
know how to experiment with that kind of stuff
Or
yet.
like even better is like, would that energy even be enough?
Well, yeah. Well, that's the Kardashev conversation. So the Kardashev scale is something that I do not want to do a disservice to the scientist's name. He was a Russian scientist who came up with Kardashev scale, and his last name's obviously Kardashev, but I don't remember his first name. And he broke down civilizations by types.
Mhm.
So a type 1 or type 0 civilization uses the energy on their planet. A type 1 civilization uses the entirety of energy produced by their planet, including the kinetic energy of the planet moving in space, which is a rather enormous amount of
Oh,
energy.
that's
A
crazy.
type a type 2 civilization uses all of the energy of their star system, including the kinetic energy of their star moving through space. A type 3 civilization uses the entire energy of their host galaxy, and a type 4 civilization their host universe.
Hmm.
So the amounts of energy that you're talking about at that point is, 2 to the 700th, 2 to the 1000th, 2 to the 10,000th. Like, you have to come up with new measurements because scientific notation stops making sense when you start adding 50 zeros after your one. So there's, but those energy levels are indicative of what would be required to do some of the things we're talking about. Like for stellar travel, moving around within your star system, fusion makes all kinds of sense.
Yeah.
Using fusion drives and things like that makes all kinds of sense. Except like we talked about, you point that drive at a planet and you blow a hole in it. So there's gotta be a level of responsibility around that. But
Just point
makes
at
all kind
Pluto. We already had that debate.
right, yeah, it's fine. It used to be a planet, burn on top, layer off. But the speeds you could reach, with a
Hmm.
fusion drive would get you from here to Mars in a couple of days, would get you from here to Pluto in a week, and granted, you'd be under gravity, at least one gravity of acceleration most of that time, then flipping midway and slowing down so that you didn't shoot off into the, interstellar space. But that's a well-established scientific hypothesis is that if you could produce the right amount of energy, you could move at that speed and we could populate the solar system, which goes back to our earlier conversation about, we have to solve the energy problem. But interstellar travel, The closest star system away, we're talking about 2, 4, 5, 6, 8, 10, 12, 15 light years. And which means if we talk about four, which is Alpha Centauri, that's 4 years the speed of light.
Right. Yeah.
So it's if if we wanted to get there within our lifetimes, we would have to move at 30, 20, 30% the speed of light. And the amount of energy it would take to accelerate anything of sufficient mass to that speed is beyond fusion. Like
Yeah.
that is a whole new level. And even then, it would still take at 20% the speed of light, it still take 30 years to get there.
So,
So
oh man. I
I
feel like this might sound dumb, but instead
have a
of
dumb
being
question.
like, how do we go faster than the speed of light? And just be like, all right, it takes, 8 years to get there. And that's, 10% of your life or whatever. Why
Right.
don't we just make people live longer? And then that 10 years is like nothing. You know what I mean? It's
So
like,
it's
okay, like think about it this way. If I lived 1,000 years, 10 years isn't anything.
so that is a common trope in science fiction. Is
Hmm.
changing lifespan, or species that have incredibly advanced lifespans.
Right.
There's a lot of authors that have played around with that. The one that I tend to lean into pretty heavily is Niven, Larry Niven, when he wrote Ringworld and then Protector. The Protectors lived 20, 40, 50,000 years. Basically, they're just immortal unless their offspring die and then they don't want to live anymore, so they just die.
Yeah.
But the concept around increasing human lifespan, I mean, that's things that we play around with here,
Hmm.
with understanding, how aging works and how cellular damage works and things like that, in a lot of our experimental, data analysis. Which is why, when we've had conversations about, SpaceX and traveling to Mars and things like that, to clarify, like I've talked about, I love what SpaceX is doing. I just don't like Musk. So let's get to space. Like let's catch rockets. Like let's get to
Hmm.
Mars. But that knucklehead needs to go sit down. Maybe stop doing ketamine for a while and let's figure out like what's actually going on with his brain. But
Could you imagine being in a K-hole in space? That'd be
no,
great.
see, there's some
That might
crazy.
be
Like
the
it's already gonna
worst.
be it's
That,
already gonna be trippy. You don't want it to get crazy with
dude, that,
like
that
just
might
falling
that might
down the
be
K
worse than
hole.
the freaking rays there's out there.
Right. You're like, I survived all the cosmic rays, but my brain's fried. So
Dude, I'll
it's
take the electromagnetic rays over a
right.
K-hole in space
Yeah,
every
no.
single time.
That's see right there. That's gonna be the catch line. That's gonna be the catch line. Like I have the most inaccurate brain, and I will take
Yeah.
electromagnetic radiation over the K hole in space. So
We're not talking black holes. We're talking
no,
K-holes, all
K
right?
holes probably worse, but it's so the building building
Mhm.
humans that are capable of withstanding the rigors of space travel
Right.
in any extreme scenario, whether it's just going to Mars, being exposed to solar radiation without the benefit of the Earth's atmosphere, or, going to interstellar travel and, being on a spaceship for 250 years. It's the solution, the problem is pretty clear. Human bodies are not designed for that. We have not evolved to that space. So how do we solve that problem? Either we go to sleep for a really long time, or we make our bodies able to withstand almost superhuman levels of damage and just continually regenerate and continue to keep going. Radioactive energy coming off of cells. You've got your alpha rays, your beta rays, and then your gamma rays. As long as it's not inside you, alpha and beta is not that bad. But gamma
Mhm.
rays will barbecue you, and to like levels of damage that are astronomically high, just like X-rays. And stars, along with most things in space, tend to put off high energy rays, just like that. So we're walking into an environment that we have not, or flying rather, that we have not evolved to be able to
Launching.
tolerate. Yeah. So we have to build ourselves into a better version of ourselves if we want to survive in space. And then we've talked about this a little bit before, but we've never even done decent experiments about how to grow and have a baby in space.
Mm.
Like how do we reproduce? What
I got a
happens when
pretty good idea on how to reproduce. Don't worry. I'm
how do you
joking.
reproduce in space? Let's just put you in space and see what happens. So
As long as you're still
so
K-hole, I think I'll be good.
right, you'll be fine. Most people survive without the KO. So we don't have the answer to that. We don't know what would happen
Mm.
genetically to the offspring. We don't know what would happen to the woman as she was carrying the baby.
Right.
We don't have answers to that. And doing experiments are largely unethical. Like, let's just put a pregnant
Yeah.
woman in space and see what happens. All right, well, you're able
Do
to
you think that
damage
giving birth
skin.
in zero G would be easier or harder? I feel like it'd be easier, but like maybe
Well,
like you can like because you don't have anything to push against. Maybe it's harder. I
yeah,
don't
but
know.
you got to think about the woman's body, which I know is admittedly difficult for you.
No,
So
I'm an
it's
expert at thinking about woman body, bro. I'm a
I contend that mightily. I don't think you're an expert at all.
accurate brain right here, buddy.
So I think, but you would it be easier? Not really. I mean, you're still pushing a very large thing out of a very small opening in a very
Yeah,
painful
yeah.
process, and it's you still got to move things out. Like we're not designed to do that. Like you have to
Mhm.
remove fluid and blood and tissue and all kinds of stuff that's happening during the process.
It's just like floating around in zero G.
That's
Oh
exactly what would happen.
God.
That's exactly what would happen. Like
Dude.
when astronauts on the space stations when they cut
Mhm.
themselves, it's a very dangerous thing. Not
Mhm.
just because they're bleeding, but because that fluid is now floating in the air and air
Oh
recyclers and all kinds of
God.
other things are going to pick it up. So these are things that aren't talked about because they're not
Mhm.
sexy. It's not
Right.
as cool as putting a big stainless steel ship up in space, but being in space fucking sucks. Like it is
Yeah.
difficult. It's all of the things we have evolved to do are hard. Now that I want to go on record and say being in space is bitching, but it's
Yeah.
hard. Like it's not, I think we should be in space more. I think we should be doing more science and more exploration and answering more questions, which is why going back to SpaceX and some of the other ships that are doing private launch or other outfits doing private launches, I think it's amazing that we're doing
Mhm.
that. We need to do that science. We need to solve those problems. But we also need to be realistic about it and realize that our bodies just aren't cut out for that. And we need to also be doing science to make our bodies better to be cut out for that. And the side effect of that, doing that science, is that we get better on Earth.
Right.
We live longer. There's less heart disease. There's less blood pressure problems. There's less diabetes. There's less, heart attack. There's all of these things get better because we make the body stronger. It's
Mhm.
if it's strong enough to live in space, it is going to kick ass down on Earth. It's not going to have any problems. So obviously, though, there's the questions about if you're going to be in space for a long time, and then do you need things that are adapted to gravity, and blah blah blah. But I think, the I think probably the animals that are adapted to very little gravity, octopus, probably do
Mhm.
pretty good in space. But then
Yeah.
again, they're still, even though they're moving in an environment that simulates not having gravity, the pull of gravity is still on them, even when they're in
Mhm.
the water. So everything, there's still a down. There's still a blood goes down, blood goes up, things move around, and so there's a lot of biological questions about that. And that in my mind, which is something that's why we work as hard as we do, is we need to answer the questions about the body to make us robust enough to be able to explore. And then it doesn't matter. Like if you live for 10,000 years, so what if it takes 50 years to get to a star? You just
Mhm.
build a ship that can make you survive that long and then just go.
Right.
So it that question then becomes what can we do within our lifetimes? And that's where the obsession with traveling at such astronomical speeds comes from. But I think before we jump off this topic, the distances are something that need to be kept in mind. Space is big. This is really big.
Yeah.
So the Milky Way galaxy, the current assumption is that the research is showing it's about 111,000 light years across. That's roughly circular. And we're kind of near an end. We're kind of out on an arm.
Wait, what?
So yeah, we're kind of out
Like the
on
third closest planet? Oh, that's
galaxy.
solar system. Cut that. Editor, cut that. That was so damn, dude. Oh,
That
shit.
was good.
I
That was
swear
fun.
to God, guys, I do have strengths
Yes, yes.
somewhere yet to be found.
One thing before I'm going to go off on a little bit of a tangent here. I'm actually going to give Shane a pretty big compliment. I have always thought that curiosity is one of the most powerful things that intellect can deliver.
Mhm.
We say all the time, "Oh, people are dumb. Oh, people are this. Oh, people are that." But the real power comes from asking the question and finding the answer.
Right.
So any of us, and I did it for a long time, that says, "Oh, well, I already know the answer." You're already wrong. Verify, check, be critical, think that it might be incorrect. Don't do this shit where it's do your own research. Trust the people that have done a ton of research and then verify that yourself.
Right.
That's how we learn. That's why we saw an explosion in intellect thousands of years ago when we started writing shit down because then we could use the knowledge of the people that came before us to grow further, to learn more, to reach further. So all 34 viewers that are watching and listening right now, Sane's not a dumb kid because he's asking the questions. Now he might not have the information right now and actually
Yeah.
think that the solar system is the galaxy, but by asking the questions, that's how you move beyond the stigma. The I'm a dumb kid, I don't know anything. It's be curious, be critical.
Yeah. I will admit that beyond all failure, even if it is like the most oblivious or obvious thing, I have never been afraid to just be like, so what's this? You know what I mean? Like even from like school or like just life in general, I feel like I've never been the type of person to be like ashamed of asking. Like
There's power.
when you're like in kindergarten or whatever, and they're like, raise your hand because like if you have a question, at least like 10 people do or whatever. Yeah, I was always that kid. I was like, hey, teacher, so how do I do 3 plus 3? You know what I mean? I was like,
Right.
so I don't know. I always felt like, and also I always felt like there's power in being like I don't want to say the dumbest, but like the least informed in the room. You know what I mean? Because like,
Well, if you are the smartest person in the room, you're in the wrong room.
yeah, that was
You
kind of
know,
my
you
thing. I always was like, I'm not afraid to ask questions. I'm not afraid to be in that vulnerable state where people might perceive you as unintelligent. And I'm also not afraid to just be surrounded by people I know are like outclassing me in whatever field they have. Because for me, I was always like, and that's a big reason why I hang out here so much is just like I always felt like I can only improve upon myself or make myself better by being in the vulnerable state or in that position where you're asking the
Well,
questions.
and there are a lot of times where Shane will walk into a room with a bunch of smart people, where the scientists and I'll be in there working on stuff and building things and breaking stuff, and Shane will just sit there quietly, fly on the wall, and then a few hours later be like, "All right, so I didn't understand shit. So tell me all these things. How did this work? What does this mean?" So and that, but that's the intellectual curiosity that I think is lacking, and when we talk about where we are at now as a culture in America, as a species in humans around the world, where there's this pursuit of excellence that's no longer associated with the pursuit of knowledge. Like I
Right.
want to be good at something, but that doesn't mean I want to know how to be good. I want to understand something, but that doesn't mean I want to learn it. I just want to magically, through osmosis, understand it. And then I'm going to grab three concepts out of that and I'm going to say I know things and I'm going to tell all the rest of you, fuck you, do your
Hmm.
research. Well,
Yeah.
the first time that you deliver that ego to someone that's walking around with a few PhDs and actually knows the topic, you get shut down because they've done their research. They've rigorously been peer reviewed. They've dealt with the damage of other very smart people taking apart their concept and learned how to defend it and learned how to do the homework beforehand to defend it when
Right.
it does happen. And the war on intellect that we currently see happening, intellect should be aspired to, but at the same time, those with it should try and share that knowledge with the
Hmm.
people that don't have it. And we're both every group in this is at fault. Those that have knowledge should try and make it more readily available and not put it behind a paywall. And
Yeah.
those that are trying to acquire knowledge should check their egos at the door. Just be like, all right, I don't know this. I want to learn more about it. Now that doesn't mean that I'm not a capitalist. I own a company. Like we're trying to make money here. Like there's not, it's- but I'm in that there are certain things that if we discover those things, if I discover a cure for cancer, I'm going to put a nominal fee on it so that we make some money and then I'm going to save some damn lives.
Yeah.
Like I don't want to make it unattainable. Even if it costs billions of dollars in research, sure, we're going to make that money back. But that goes back to one of my favorite quotes in the third Iron Man movie. Yeah, you can go and build as much armor as you want, but he's just going to come up with a better idea because he's Iron Man. He's
Yeah.
just going to keep doing it. So back to our space conversation. I think that comes down to, a lack of clarity and concept. But what we were talking about, Shane, is that the galaxy is 111,000 light years across, which means if
Mhm.
you were going the speed of light, it's still 111,000 years to get to the other side. So if you're
Oh
going
God.
10 times the speed of light, so warp 10, hypothetically, although warp 10 is a factor, so it actually gets
Yeah.
bigger faster. But if you're going 10 times the speed of light, it's still going to take you 11,000 years to get across to the other side. If you're going 100 times the speed of light, it's going to take you 1,100 years to get to the other side. That's if you're going 100 times the speed of light. You never slowed down. You never had to refuel. You never had to change direction. You went an absolutely straight line.
Zero
This
flat
could,
tires, zero calls to
right.
AAA.
Yeah, no problems at all. 1,100 years to get to the other side. So if we wanted to cross the galaxy in a year, we would have to go 100,000 times the speed of light, and it would still take a year.
Yeah.
Then you're at the other side. What if you're out of fuel?
Oh God. I don't even want to think about that.
So it's whatever your fuel is, whether it's energy, black hole energy or whatever it is. So these distances are so enormous. And we're not even, that's our galaxy. The Andromeda galaxy is 100 million light years away. It's way more than that. I don't actually have the statistic in front of me. I was trying to take pictures of it the other day. I probably should have written it down. But crossing intergalactic space, if you're going 100,000 times the speed of light, it's still going to take you a million years. So to cross those distances at that speed,
Mhm.
you have to get into the tens of billions of times the speed of light. Light
Right.
speed in intergalactic space is slow as hell. Like it's like you're not getting anywhere. So we're sitting here talking about, oh, well, we're going to try and figure out fusion. We're playing in the fucking sandbox. We're not even got the toys out. We're not even out of diapers when it comes
Yeah.
to space, which means we need to do the things that SpaceX is working on and that Blue Origin is working on. We need to start experimenting. We need to do the science. We need to not cut funding to precise atomic measurements so
Mm,
that we can actually measure things at very small levels, because then we can scale it up to very big levels and start
right.
doing very interesting things with it. So, this idea behind reducing the pursuit of science and education, I mean, at the risk of starting an actual flame war, because I'm talking about the start of a war and the end of one, if we hadn't dumped a ton of money and time and really smart people into the Manhattan Project, Oppenheimer wouldn't have figured it out. We wouldn't have had nukes. We wouldn't have been able to do any of these things. And that is arguably the most powerful tool that we have in our arsenal, not just as a weapon, but as an energy source and as the science that's associated with it. So that's the Manhattan Project, billions of dollars. And now what we're doing is dumping it into artificial intelligence, which a lot of scientists are currently saying, and you can Google these articles, that we are not going to get AGI from the current tree that we are barking up. So the assumption is that we're going to get it. And we're going to dump $500 billion into it and spend all kinds of money all over the place. What's that going to do? What's that going to net us? Are we going to get an atomic bomb when we're done? Because the odds right now are saying no. So why are we cutting science in other places? We got to do energy. We got to do
Mm,
biology. We got to do environment. Whether you're a climatologist or think that climate change is fake, let's figure it out. Let's answer the question. Let's get some actual
right.
definitive results. The only way you're going to do that is funding science.
It's true. Well, to wrap it up, even if you could travel through space, it would take a really long time to go a really long way. So enjoy the planet you got and enjoy the time you have here because even if you could go to Mars or some or the other side of the galaxy, it would still take you 110,000 light years. So with that, enjoy Earth. Signing off. Captain Space. I don't know. Never mind. Cut that.